Morning. We'll start the discussion on noise, which is very important in the courses related to communication. So, what is noise? Unwanted waves that tend to disturb the transmission. Unwanted waves that tend to disturb the transmission and processing of signals is known as noise. Now, what are the sources of noise? The sources of noise can be external to the system, for example, atmospheric noise, and it can also be internal to the system. So, what is the noise which is internal to the system? Example, noise that arises from spontaneous fluctuations of current or voltage in electrical circuits. And examples of this type of noise which are internal to the system are short noise and thermal noise. What is short noise? Short noise appears in electronic devices due to random behavior of electrons and holes. So this basically appears in electronic devices due to random behavior of electrons and holes. So what are these electronic devices? For example, vacuum tubes, semiconductor devices, photodiode, transistors, etc. So the keyword here is short noise appears in such devices due to random behavior of electrons and holes. Next, what is thermal noise? The electrical noise arising from random motion of electrons in a conductor. This is in a conductor. The means, now we'll see how do we calculate this thermal noise. The mean square value of thermal noise voltage VTN appearing across the terminals of a resistor measured in a bandwidth of delta F hertz. What exactly are we trying to understand here? Why are we saying it is mean square or mean square value? First of all, this once we start talking of the noise, we have to understand that it is random in nature. So whenever something is random, not deterministic, we always measure it in terms of, like, statistically we characterize the randomness in terms of it could be mean or it could be standard deviation, etc. Okay, so here, because noise is random in nature, for to measure it, to compute that, we make use of the parameter that is mean square value. That's why the word mean comes. That means the average. So mean square value of the thermal noise voltage VTN appearing across the terminals of a resistor measured in a bandwidth of delta F hertz is given by, you are already aware of this parameter E, expectation. It is expectation of VTN square. What is VTN square? It is the square voltage and this is mean. So mean square value of the thermal noise voltage. Mean square value of the thermal noise voltage denoted with E of VTN square is given by 4 times KTR delta F whole square. Why whole square? Because it is mean square value of the noise, the thermal noise voltage. So units is whole square. And here, what is K? K is Boltzmann constant, which is 1.38 in 10 power minus 23 joules per Kelvin. T is absolute temperature in degree Kelvin, and R is the value of resistance in ohms, and delta F is the bandwidth. The mean square value of the noise current. This was for thermal noise voltage. Now this is the expression for calculating the mean square value of the noise current. So expectation of, because it is noise current, it is expectation of ITN square is equal to 1 over R square expectation of VTN square, which is 4 KT R delta F divided by R square. So R and R will get cancelled. We'll be left out with one more R in the denominator. So that is G is equal to 1 over R, which is conductance. So finally, expectation of ITN square, that is mean square value of the noise current, is given by 4 kT. Instead of R, now we have G delta F, unit is amp square. We'll just take a look at a few problems, numericals. First one, a resistance value 10 kilo ohm is at temperature 17 degrees centigrade. An RMS voltmeter of bandwidth 100 kilohertz is connected across a resistor R. What is the reading of the voltmeter? So all the values are given here. It's direct substitution problem. Resistance value is 10 kilo ohm, temperature 17 degrees centigrade. So you have to convert it into degree Kelvin. So temperature is 273 plus 17, which is 290 degree Kelvin. And the bandwidth, RMS voltmeter of bandwidth 100 kilohertz. So the delta F here, this delta F is 100 kilohertz. 100 kilohertz is connected across this RMS voltmeter of bandwidth 100 kilohertz is connected across a resistor R. What is the reading of the voltmeter? So reading of the volt, this is actually the formula to compute the mean square value. But we want to know the reading of the voltmeter, which will be in volts. So we have to take square root of this. Square root of 4 kTr delta F. Square root of 4 kTr delta F, or here it is B. Both are, B also indicates the bandwidth. We know Boltzmann's constant, we know temperature 290 degree Kelvin, value of resistor 10 kilo ohm, bandwidth 100 kilohertz. So just substitute everything, compute square root, you'll get VRMS as 4 microvolts. Similarly, second problem, two resistors 28 kilo ohm and 51 kilo ohm are at room temperatures 290 degree. That room temperature means it is, even if the value is, temperature value is not given also, you can assume it as 290 degree Kelvin. Calculate for a bandwidth of 100 Hertz, the mean square value and RMS value of thermal noise voltage for each resistor, for two resistors in series and for two resistors in parallel. Similar to the previous problem, just a small extension, like not just for one resistor. Here the question is to compute the mean square value and RMS value for two resistors in series and in parallel. So we know how to calculate equivalent resistance when the resistors are connected in series and in parallel. So by just replacing R by R1 plus R2 in case of series, and R1 R2 by R1 plus R2 in case of parallel, you will be able to solve this. And finally the answers are given here. For each resistor separately, we are given 28 kilo ohm resistor, 51 kilo ohm resistor. VRMS values are given here. You can also write down the mean square value. I haven't given here. And similarly, for two resistors in parallel, C bit, two resistors in series, B bit. Okay, I hope it's clear.